Hello and welcome to another video on my channel. In this video I'm going to continue the discussion on symbolic functions and how to implement them in Java. And if you recall, our approach was based on taking advantage of operator overloading. Our goal was just to develop a univariate function space, so functions that are basically functions that take only one variable, which we called it x. So x is basically the basic math function that we define, and it's the identity function. And then all other functions such as constant function, sine, cosine, and other functions are defined as well. And all these specific functions are extending the superclass, which is an abstract function, and the operator overloading behavior is defined in this abstract function. Okay, and we looked at the implementation of the get value, because each function should be able to return the value of the function at any real number at any given point, and also a diff. And our approach for implementing a diff was to return another function. So the diff of a function is also a function. And we also mentioned that the constant function is the only function that is implementing the value of simple factory method, because you cannot assign a primitive to for example, a sine function. You can only assign a primitive to a constant function, fc function constant. And if you recall, the value of factory method was a static method. Okay, now a few useful mathematical rules, especially if we want to implement a differential, is that the derivative of f plus or minus g is f prime plus minus g prime. The derivative of multiplication is f prime g plus f g prime. The derivative of division is f prime g minus f g prime over g squared. And there is also the important chain rule, which goes into the composition, which deals with the composition of functions. And this is the topic that we are going to discuss in this lecture. So if you recall, we defined elementary functions as a no-arg constructor. So basically, when I say, for example, new sign and create an object, this create a sign of x. Basically, the meaning of this is sign of x. But what if we want, for example, sign of 2x, right? So this is the other thing. So no arg constructor means, our definition was to have a basic sign or basic function that takes the variable x. Okay, but then how do we implement the composition, or how to take care of compositions? For example, if I have g of x and f of x, now I want to calculate f of g. So f and g are functions and x is the variable, and this is called the composition. And the question is, how do we implement this? Now there are I guess two ways to do this. One is through implementing these in the constructor of the function. What do I mean by that? So when I say new sign, if there is no arg constructor, there is no arg in the constructor, or we invoke the no arg constructor, it should mean that we're passing it x. So this is the basic function. But if we, for example, write new sign of some function, let's say f, then basically this should return sign of f of x. We can do this, and this is the approach that makes more sense. Another way of doing taking care of the composition is what we actually did last time, and we use the composition. We use the utility class when we assigned a static utility methods to implement functions, and we said that if we pass a function to those utility methods, then we have to take care of the composition. But now instead of doing that, we want to implement the composition using the constructor. So let's try using the constructor, and let's head to Eclipse and investigate this. Now, if you recall from our Symbolic Math project, we implemented the abstract function, which is the parent function, okay? And we had basically two abstract methods, which defines these two methods define the behavior of each function. So get value and Deef, which returns a function. And then we had the operator overloading functions, which were basically add, reverse, add to a function, add, reverse to a function, subtract, reverse, multiplication. And for all these, we actually implemented the chain rule, because we said that for addition to basically we implemented the differentiation rules, the differentiation of f plus g, for example, differentiation of f times g, okay? We said that if a function is multiplied by a function, not only the values get multiplied, but we have to also implement the differentiation, okay? And then we implemented the sign, and if you recall, the sign basically has no arg, so public sign, it's a no arg constructor. And let's also add the documentation. So this is sign of x, trigonometric function f of x equals sign of x. Operator overloading is supported, okay? And now what we want to do here is have another constructor, public sign function f, okay? Now what we want to do is if this no arg constructor is invoked, no arg constructor is invoked, or composite constructor, let's call this composite constructor, no arg constructor, okay? If this one is invoked, we have to because right now the get value and the Deef are based on the no arg constructor. So if this is invoked, then we want to take care of the fact that this constructor, the composite constructor, is invoked. So the way I'm going to do it is by defining a basically private function func, or maybe composite func, okay? And it initializes to null. And then if this constructor is invoked, I call the composite func and just make it equal to f, okay? And then in the get value method, I check if the composite func equals null. If it's null, it means basically no arg constructor was invoked, no arg, okay? And whenever the no arg constructor is invoked, I make sure that the composite function is null, okay? If the composite function is not null, what I'm going to do is basically I'm going to return math.sign of composite func get value at point x, okay? So what happens, we calculate the sign at the basically the value of the composite function. Now for the Deef, it's the same thing, so let's write it. If composite func equals null, if it's null, what we're going to do, it means no arg constructor. If it's not null, it means a composite constructor was invoked. else in the diff we have to implement chain rule, okay? And the way I'm going to implement chain rule, I have to return a function. So in the chain rule we say that compose func.diff times basically new cosine of compose func, okay? Because I already know that the different diff derivative of sine is cosine, so I invoke the basically the composite constructor of cosine. But right now it complains because I haven't implemented the composite function, the composite constructor for cosine. The constructed cosine of the function is undefined. So let's head to cosine, and here we have the public cosine, and because this composite function is basically going to be shared amongst all the subclasses, I'm going to just put it here. And instead of having it private, okay, this is still complaining because the private field is not visible, so I have to go here and make it protected. Okay, so we have this protected field composite function. In theory I could implement the composition somehow here in this abstract class, but it's better to let the subclasses, which are specific concrete functions, to implement this to implement the composite constructor. Okay, so we have this no arg constructor, and then we want to have another constructor which is composite constructor. So public cosine, we pass in a function f, and then here we say that composite func should be null, we enforce this, and here we say that composite func should be f, okay? And here the same thing, if composite func is null, it means the no arg constructor was invoked, and else it means the if the composite function is not null, it means the composite constructor was invoked. Composite func basically get value at x, okay? The same thing here. So diff of cosine is minus sine, so we say that if composite function is null, just return minus new sine with no arg, okay? Remember, this minus works because we have already implemented the operator overloading for negation. However, if let's also give this an indent, else, so if the composite function is not null, we have to implement the chain rule. So return composite func.diff times basically maybe minus new sine of composite func, okay? And the problem, let's also put this minus sign maybe here to make it look nicer. All right, so what happens here, the diff of cosine is minus sine, cosine of function is f prime times minus sine of the function, okay? Now let's go and test our theory. So I'm going to create a new test class called maybe outside, maybe in another package. So let's create another package, tests, and move our test func there, and then This is complaining for the argument types. Let's see why. So in the function, alright, so we have to define right now. All these operator overloadings have a package level access, right? These are so these filled blue triangles. It means because they're filled, the inner of this triangle is full. It means it's a method, and blue triangle means it's a package level access. So we have to make these public. So in general, it's a good idea if it's part of the API. We want to make all these operator overloading methods public. I'm just quickly type these. Yeah, I'm just trying to quickly type public here. Okay. Maybe let's just copy this and public, 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 public divide, and public negate. Okay, now yeah, our test function is not complaining. Let's create another class, test composition, and let's create a main method. So let's create a function. F sign is maybe f1. F1 is a new sign object. Okay, we need to import these. Okay, next is function f2 is maybe let me see, what else did we implement? Sine, cosine, ABS, x, new, let's say new x. Okay, and we have to also import x. And then but right now we can also write this new sine new x. Okay, and this works. Before it didn't work because we didn't have a constructor that had a function. So basically f1 and f3, this is also sine of x, right? f1 is also by default is sine of x because we're invoking the no-r constructor, and this is just f of x equals x. So let's check this system.out.println f1 get value, and in the get value we are going to write math.py over 2, which should return 1. And then we do the same thing for f3. 1 1. If we write pi over 4, should be 1 over square root of 2.707. Okay, so now the composite constructor also works. Okay, note that we don't do the composite constructor for x because x is just identity. It doesn't make sense. If I want to have x of something, x of a function is just that function. We don't need to use composition. But we can do that just to make sure everything is the same. All subclasses have the same structure, but really mathematically we don't need to do that. All right. Let's say we implemented sine and cosine, and let's head to our function math, which was the utility class. And if you recall, our approach in order to make writing these functions more natural was to define the variable as the static function, okay, public, and it should be also final. So and let's also make our utility class final. So when we make it final or make the constructor private, it means this class cannot be instantiated or extended. So this is just a utility class. And so basically if we write function f4, and what I'm going to do before that, from import static function math, everything, we can just write sign of x. Okay, so sign comes from the utility method, which represents the sign class, and then x comes from the utility object for utility function math class, which represent our variable, which is the identity function. Okay, this is a very nice and natural way of writing our equations, our expressions, right? So this is more like natural way of writing things in math, right? But if you recall what we did here, we only, so before adding the Deef functionality, we just said that we can use anonymous classes, and if we pass a function, we can just use anonymous classes and override the get value. Remember that sign is a subclass of function, right? The no arg. But when we use anonymous class and use the super keyword, super here refers to the sign class, right? If I bring my Eclipse on, so this super class doesn't refer to the function class, it refers to the sign class. Okay, and we said that the approach for this anonymous class thing was to call the get value method of sign using the super, but passing the value of the inner function. Now if you, as you can see, now that we implemented the, for the composition, now just use the composition constructor. So instead of doing all that anonymous class, we just write return new sign of func. It works. And because we already implemented the Deef, also Deef, we don't need to do anything weird here. So same thing with cosine. So I just write new return new cosine, but now I invoke the composition constructor and pass it the func. Okay, so this is a much cleaner way of developing this basically this utility class. And let's also try or test the Deef functionality. So f4 is sign of x, system.out.println f4, and I guess we did not implement the, we could implement the toString method, but for now let's maybe let's just quickly and go and override the toString method. We just put x, and then for the sign we just write sign of x. And for the sign, what we're going to do is %s.format and we're just going to say that print composite function to a string, something like this. or maybe let's break this down, plus composite function to a string plus this. Okay, and sine of x, let's see what happens here. It prints sine of x. And let's go for the cosine. We do the same thing. So basically in the toString method we're also adding the actually we should check if composite function is null or not. Return basically sine of x, else return this. So this is the general template for toString method for our functions. For cosine we just have cosine, cosine, composite function. Okay, and then function utility, let's try. So sine of x, it should return sine of x, no problem. Let's try system.out.println cosine of x, and the cosine of x comes from the utility class cosine of x. Okay, now let's try system.out.println sine of cosine of x. What happens here? Sine of cosine of x. What if I write sine of cosine of 2x? It doesn't work because 2x, so 2x is still more like x, so we have to go and implement the maybe get 2x. Okay, so we go and do the composite function for these two. So and the way we're going to do it is okay, let's add the public x and composite func equals null, and public basically x function f, composite func equals f. Okay, and in the get value we check if composite func equals null, we return x, else we return basically composite func dot get value at x, because it's the composition of an identity function. And in the Deef we say that if composite func is null, return a constant function, return else, return composite func dot Deef. Okay, and finally for the toString method, if composite func is null, return con x, return x, else return composite func to a string. Okay, let's see now if the 2x method works. It still doesn't work, and I'm wondering why it doesn't work. So we have the cosine, this function. Alright, let's see. Function. But before getting to that, let's just, for this lecture, let's just quickly test the Deef functionality. So system.out.println sine of x, and then system.out dot print line sine of x dot diff. Let's see what happens now. Sine, but when it goes to diff, and the reason for that is that what happens here is that it returns the function, not a specific function. So the compiler doesn't know the return is actually a cosine. It just knows that it's a function, the abstract function, right? So we're going to fix this in the next video, but for now, to make sure that this is correct, we can get the value at math.pi over 2, and cosine at pi over 2 should be 0. Okay, and the sine at pi over 2 is 1. Yes. And then what happens if we have a, for example, sine of x diff? So what we should get is cosine of x times cosine of sine of x. Okay, so system.out.println f5.getValue. If I calculate this at let's say pi, what happens? So cosine of pi is -1, sine of pi is 0, and cosine of 0 is 1. So we should end up with -1. Yes. Alright, thank you for watching. In the next lecture we are going to take care of the string representation of our function space, especially when we are dealing with composition of functions. Thank you, and I'll see you next time.